Now we are going to look at principles of counting. The fancy name for this term is combinatorics. So what are we going to do in this chapter? It's, as the name suggests, we are just going to count things. And there is almost no theory in here. All we're doing is different tricks of counting things faster. You really don't have to use anything. If you want, you can just count things one by one, like we did. Like say you want to find what are the number of elements in a power set. Well, you can just literally write down the entire power set and then count the elements one by one. So in theory, you don't need to know this chapter at all. You could have just done all the counting by yourself. So what we're going to do in this chapter instead is just find tricks to speed up the process. So everything we do in here is completely optional. You don't have to follow any of these methods. If you can count very fast in some other way, then you can do that. So what we are learning is just tricks or principles of counting faster. There's no theorem anywhere in here. So that is what this entire chapter is about. Just tricks and principles for counting faster. All right, with that preamble, let's start with the first principle. The book uses the word rule. I don't like that word. Rule suggests that you have to follow this rule, otherwise you will get something wrong. That's not what it is. It's just a trick. We are using a trick to make the process faster. So it's up to you if you want to use that trick or not. Or a principle. It's up to you if you want to use the principle or not. So the first principle we'll learn is the bijection principle. It is very straightforward yet extremely powerful. And what does bijection principle say? If two sets if there is a bijection between two sets S and T, then they have the same number of elements. And recall, what does it mean for something to be a bijection? The way we defined bijection was 1 to 1 and on to. So if there is a function f from S to T, which is a bijection, that is, which is 1 to 1 and on to, then they have the same number of elements. Another way to describe a bijection is by saying that the function has an inverse. So if I have a function f from S to T, which has an inverse, then it is a bijection. And then again, we can say that S and T have the same number of elements. Very simple principle, but now we can use this principle in a very smart way to count the number of elements in a power set. So what we'll show is that if a finite set has n number of elements, then the cardinality of the power set is 2 to the n. And this is a trick. Trick that we are going to do is we are going to use the bijection principle. It's a trick. Somebody thought of it. It's a clever idea, and so we get a very nice answer. It's very hard to motivate it, and I don't expect you to come up with this trick on yourself. So with that caveat, what is the trick? So I want to show that the power set has 2 to the n elements. So what I'll do is I'll construct a set T such that T has 2 to the n elements, and then we'll construct a bijection from the power set of S to T. And because of this, then power set of S will have the same number of elements as T, which is 2 to the n. And that will give us the required result. And what is the set T? The set T is going to be binary strings of length n. Which is 0, 1 to the n. And you can see that size of T a size of 0, 1 to the n, which is 2 to the n. So T does have the required size. What's missing is the bijection from PS to T. And this is a clever bijection. Instead of giving a detailed proof, which is really involved, it takes a while to write this proof rigorously. I'll just give you the construction of the bijection. All right, so what are we trying to do? Let's suppose S contains n elements A1, A2 up to AN. And now I want to construct a function that goes from power set of S to T, where T is 0, 1 to the n. I'll just use 0, 1 to the n. So what does that mean? That means I need to take an element of the power set and give you a binary string. Now, an element of a power set is just a subset of S. So I need to start with U, which is a subset of S. And I need to give you a binary string of length n. And the way we'll do this is as follows. So a binary string of length n is nothing but a sequence of digits b1, b2, bn, where each bi is either 0 or 1. Okay, so what I'll do is I'll look at each of the elements a1, a2, an. One by one. And if A1 is in U, set B1, or A, sorry, if AI is in U, then set BI equals to 1, else set BI equal to 0. So I look at each element one by one. So I'll start with A1 and I'll see if A1 is in U. If A1 is in U, then I'll set B1 to be 1, otherwise I'll set it to equal 0. Now go to A2. If A2 is in U, then I'll set A2 to be 1, otherwise I'll set it equal to 0. Let's do a concrete example to explain what the bijection is exactly doing. Suppose I consider the set with just 3 elements. Then my goal is to construct a bijection from power set of S to 0, 1 to the 3. And I can do this explicitly as follows. So first, let me list all the subsets of S. So these are my subsets. Now I want to construct for each of these sets a binary string. And the way I'll do this is I'll look at A1. If A1 is in the set, then I'll put 1 in the first place, otherwise I'll put 0. So let me just do this. So now my focus is on A1. For the first one, A1 is in there. So my first digit is 1. Second one, it's still there. Third one, yes. Fourth, in this set, there is no A1, so I'll put a 0 in the first place. That's my first digit. Then for the second digit, I'll look at A2. So in the first, I have an A2, I have an A2, I don't have an A2, I do have an A2. And now I'll focus on A3. And if A3 is there, I'll make the third digit 1, otherwise I'll make the third digit 0. And that's my map. Now one can show, if you have the patience, that this is both 1 to 1 and on 2. In this example, you can explicitly see that every single binary string of length 3 occurs on the right hand side. So it's on 2. And you can see that any 2 different sets are going to 2 different things. No 2 sets map to the same thing, so it's 1 to 1. And so it is a bijection. And so what we have done is we have constructed a bijection from PS to 0, 1 to the 3. And so they have the same number of elements by the bijection principle. And there's nothing special about 3. This method works for any n. And so we get that the cardinality of the power set is 2 to the n. Of course, it's tedious to prove that this function that we're constructed is one-to-one, but you do have to prove it to have a rigorous proof, which then gives the required result. But like I said, this chapter is not really about theory. This chapter is just about finding fast tricks to count things. And so we won't do the proof in all the details.